Okay, here's the fourth video from Chapter 4. And in this video I'm going to continue the discussion of optical fibers, and in particular step index fiber modes. And so in the previous video we saw the mode diagram for step index fibers. It's kind of complicated with all the different modes and all the different geometries. However, generally we're interested in this lowest order HE11 mode. And it has more or less Gaussian profile and exists for V values or normalized frequency values of less than 2.4. So there's two things I'm going to do here. I'll show you number one, the approximate equation for the number of modes, and I'll also show you an empirical relation for the spot size of the mode relative to the core radius. So first, the approximate number of modes. For V substantially larger than 1, we're going to have that the approximate number of modes, n, is something like V squared over 2. And just to give you an idea, if we have step index fiber with a 50 micron core, that's 5125 in this example, with core index 1.48, cladding index 1.46, and operating at a wavelength of 820 nanometers, typical of a low-cost LED for a multi-mode fiber application. This is multi-mode fiber with that large 50 micron core. Using this equation and the definition of the normalized frequency V, where we plug in the indices, the wavelength, and the core diameter, we're going to get 1,078 modes. This is a large number of modes, and it is in fact typical of the application of multi-mode fiber with these short wavelengths. Okay, so that's an example of using that equation. You can reproduce that calculation if you like. Another equation that really helps us characterize that zeroth mode, or that lowest order mode, HE11, is the following. What we're going to do is we're going to write down the mode field radius, W, and call it the spot size. We're going to do that in exactly the same way that we did in Chapter 2 when we talked about the Gaussian beam profiles. So let me remind you of that. I'll remind you of a slide from Chapter 2 and a slide from Chapter 4. First of all, the slide from Chapter 2. Recall that when we talked about diffraction, we talked about a Gaussian beam, which had been brought to a focus. And it turns out that if the input is a Gaussian beam, the output is also a Gaussian beam. And we could calculate the width of the output Gaussian beam based on the width of the input. And when we draw that Gaussian beam profile, we use W to be the spot size, which characterizes the width of that Gaussian, using this equation up here. Okay, so W is the spot size in exactly the same way that we used it in Chapter 2. And we're using a Gaussian beam approximation to the lowest order mode because it really does work. If you'll recall our slide from Chapter 4, where we looked at the modes of the symmetric slab, and the lowest order mode did have an approximate Gaussian profile here. Okay, so the lowest order of the slab has an approximate Gaussian profile, and likewise the lowest order for the optical fiber also has an approximate Gaussian profile. So that W parameter, the mode field radius, or the spot size, is of great interest. And what this equation is an empirical equation valid for a limited range of normalized frequencies, V, and it says that the spot size divided by the core radius is 0.65 plus 1.619 v to the minus 3 halves plus 2.819 v to the minus 6. This is an empirical relationship. It's not something that we're deriving from first principles, but it's a good fit in this range of normalized frequencies. And I've shown the plot down here, at least a rough plot. And what it shows is that as the normalized frequency ranges from 1.2 up to 2.4, the normalized spot size goes from 3 down to about 1.1. And this is exactly consistent with our understanding of mode confinement. W over A characterizes the confinement of the mode. When W over A is approximately 1, or a little bit larger than 1, we have a well-confined mode. I'm sorry. Let's just say approximately 1. We don't want it to be greater than 1. Or too much greater than 1. We're going to say when W over A is approximately equal to 1, we have a well-confined mode. When W over A is greater than or about equal to 2, we have poor confinement. Okay? And so this illustrates the mode confinement for that lowest order mode. It turns out that when, well, it's consistent with what I said above here. For V greater than 2, we have good confinement and low loss. Okay? One thing you can do with this equation is, suppose we're given the characteristics of the fiber. Suppose we know N1, N2, and the wavelength and the core radius of the fiber. Okay? From N1, N2, and the wavelength and the core radius, we can calculate our normalized frequency. And from that, we can calculate the W over A ratio. And then, knowing A again, we can calculate the spot size. So this is a nice way of actually being able to calculate the spot size of that lowest order mode in a step index fiber. Okay, so this is these are two equations which are important, more or less empirical, sort of rough, but give you good approximations for the spot size and for the number of modes. For the spot size of the first mode and for the number of modes when we go to multi-mode behavior. So that's the summary of step index fiber modes. Thanks.